Welcome to my lecture series on the chemistry of main group elements. In my previous lecture, I was discussing about the classification of main group compounds, and I had mentioned that all compounds of main group elements can be simply classified into three categories: main group hydrides, main group oxides, and main group halides. So, I had stopped while discussing about main group halides. So, let me continue from where I had stopped. The halides of main group elements are an important class of compounds, and with the exception of lithium and beryllium, the S block halides are essentially ionic in nature, and the P block fluorides are predominantly covalent. And of course, exceptions are always there, and here exceptions are those of nitrogen, oxygen and sulfur, where only the lower oxygen state halides are formed. And in case of D block elements, they form halides with a range of oxygen states. The higher oxygen state halides are formed especially with fluorine and chlorine. I had already mentioned that fluorine is capable of stabilizing any element in the periodic table in its highest possible oxygen state, and the lower oxygen state halides of main group elements are essentially ionic solids. The higher oxygen state chlorides formed predominantly by the 4D and 5D series elements, and which are covalent, and there is an increased tendency to form cluster compounds with metal-metal bonds. So, our interest is only focused towards the main group halides. So, let us not worry too much about the transition metal chemistry, and let us look into some important periodic properties and also some entities we come across while discussing the classification and periodic trends. The important term we come across is covalent radii. What is covalent radius is one half of the distance between the nuclei of two covalently bonded atoms of the same element in a molecule is taken as the covalent radius of the atom of that element. Essentially, in a neutral homodiatomic species, the distance between the two nuclei is essentially the covalent diameter, and half of that one will give you the covalent radius of individual atoms. The distance between the nuclei of two hydrogen atoms in H2 molecule is 0.74 angstrom units. Half of this distance, that is 0.37 angstrom unit, gives the covalent radius of hydrogen atom. And you can see here how to determine the covalent radius. For example, you take a diatomic molecule shown like that, and the distance between the two nuclei will give you some information about the covalent diameter, and now this half the distance is what we call it as covalent radius. So, one can calculate the covalent radii of other elements from the internuclear distances of the elements whose covalent radii are known. For example, if you consider methane, I can simply write in this fashion. And the internuclear distance between these two, carbon and hydrogen, is 1.14 angstrom units. So, in this we know the internuclear distance of carbon and hydrogen is 1.14 angstrom unit, and also we know the covalent radius of carbon, that is 0.77 angstrom unit. From this one, we should be able to tell what is the covalent radius of hydrogen atom. So, that means simply subtract 0.77 from 1.14, that essentially gives you 0.37 angstrom unit. This is essentially the covalent radius of hydrogen. So, this is how the covalent radius of unknown atom can be calculated just by measuring the internuclear distance and knowing the covalent radius of one of the atoms. So, this periodic table what I have displayed here shows the trend in covalent radii. For example, if you see here, the covalent radius is increasing down a group and decreasing across a period. Of course, the reason we already discussed it. So, let me not elaborate more on this one. What one should remember is the covalent radii decreases across a period and increases down a group. And let us look into the ionic radius. The distance from the nucleus of an ion up to which it has influence on its electron charge cloud is essentially termed as ionic radius. I repeat again, the distance from the nucleus of an ion up to which it has influence on its electron charge cloud or electron density is essentially termed as ionic radius, and a cation results from the loss of one or more electron from the outer shell or valence shell, and cation is much smaller than the corresponding atom. For example, if you consider the atomic radius of sodium, that is 1.54 angstrom unit, whereas the ionic radius of sodium plus ion is 0.95 angstrom unit. And when we talk about anion, that results when one or more electrons are added to the valence shell of an atom. Anion is much bigger than the corresponding atom. You can see clearly in case of chlorine, the atomic radius of chlorine is 0.99 angstrom units, whereas the ionic radius of chloride ion is 1.81 angstrom unit. So, this gives you about the relative sizes of ionic radii versus atomic radius, and also between ionic radii and covalent radii while considering the both for the cations and as well as anions. So, let us look into the sodium. For example, sodium when you remove an electron, that generates a cation, and similarly chlorine on addition of an electron it generates an anion. And I have shown in this cartoon here Na plus is there and it interacts with much larger chloride ion to form NaCl, and this NaCl this internuclear distance is shown here, and this internuclear distance will give you the total sum of the ionic radii of sodium ion as well as chloride ion. So, another term I am going to introduce is isoelectronic species. So, what is isoelectronic species and how the ionic radii vary among isoelectronic species can be seen here. So, isoelectronic ions are those which have the same number of electrons, but differ in the charge on their nuclei. Let us look into this series of isoelectronic species I have given here. Let us look into this series. Here nitride anion is given N3 minus and oxide is there O2 minus, and fluoride F minus and Na plus and Mg2 plus. If you just look into the nuclear charge now, nuclear charge essentially 12 in case of magnesium, 11 in case of sodium, and 9 in case of fluorine, 8 in case of oxygen, and 7 in case of nitrogen. Now, basically out of 2 valence electrons from magnesium, 2 have been eliminated to form magnesium 2 plus, and the 1 valence electron is taken from sodium to generate Na plus, and then similarly 1 electron is added in case of fluorine, and 2 electrons in case of oxygen, and 3 electrons in case of nitrogen to generate this isoelectronic series. In this isoelectronic series, if you just look into it, the number of electrons is confined to number 10. In all these compounds, we have total 10 electrons are there. That means they have the neon electronic configuration. And here look into the ionic radii now. In case of nitride anion, it is 1.71. In case of oxide, it is 1.45. In case of fluoride, it is 1.33, and in case of sodium cation, it is 0.95, and in case of divalent magnesium, it is 0.60. And now the question is why this ionic radius is decreasing in this order. So, that information comes if you just look into the effective nuclear charge. The nuclear charge increases from sodium to magnesium ion. The electrons are held more and more tightly by the nucleus, and as a result the ionic radii decreases. Generally the ionic radius increases down the group and decreases across a period that we saw in the previous slide. And so, another term we should be familiar while discussing chemistry is van der Waals interactions and van der Waals radius. So, what is van der Waals radius? So, van der Waals radius of an element is half of the distance between the two atoms of that element which are interacting through van der Waals forces without making a formal chemical bond. I repeat again, van der Waals radius of an element is half of the distance between the atoms of that element which are interacting through van der Waals forces without making any formal chemical bond. So, how to visualize that one? Let us look into this cartoon here. Let us assume there is a diatomic molecule is there and another diatomic molecule is in its close vicinity. And now, whatever the dotted line that shows the distance between the two nucleus through van der Waals interaction, and now this distance, half the distance is essentially called as van der Waals radius. Van der Waals forces are the weak forces which contribute to intermolecular bonding between the molecules. Example, hydrogen bonding, dispersion forces, dipole-dipole interactions, London forces, etc. And covalent radius is smaller than van der Waals radius and covalent bond is much stronger than van der Waals forces. Van der Waals radius and covalent radii of some elements I have given here for better understanding. For example, hydrogen, nitrogen, oxygen, fluorine and chlorine, both covalent radii and van der Waals radii are given here. You can see the covalent radii is about 0.37, 0.75, 0.73, 0.72 and 0.99 respectively in case of those elements shown there. And if you just look into the van der Waals radii, that is almost 3 to 4 times more in case of hydrogen, and at least it is the double the what measures as covalent radius. So, that means essentially van der Waals radii are much larger compared to covalent radius. Let us look into some questions here. Account for the decrease in the first ionization energy between phosphorus and sulfur. So, the question is account for the decrease in the first ionization energy between phosphorus and sulfur. Let us look into it. First, what we should do is, first we should write the electronic configuration for both phosphorus as well as sulfur. Instead of writing 3p3, for simplification and better understanding I am writing 3p1, 3p1, 3p1. Similarly, let me write for sulfur as well. So, if you just look into the electronic configuration of phosphorus and sulfur, this is very similar to the case of nitrogen and oxygen. In case of nitrogen, what we have is 2s2, 2p3, and in case of oxygen, what we have is 1s2, 2s2, 2p4. So, that means in p orbital we have 3 electrons in case of phosphorus, whereas 4 electrons in case of sulfur. So, that means in case of sulfur we have one extra electron and that is paired up in one of the p orbital, and here the interelectronic repulsion between these two electrons is considerably more compared to the situation in phosphorus. As a result, what happens, by losing one electron, sulfur readily attains half filled electronic configuration. That means I can write S plus So, this is similar to what we come across in case of phosphorus. So, because of this one, what happens, it is very easy to remove the electron from sulfur to make it S plus, whereas in case of phosphorus or in case of nitrogen, since we have half filled electronic configuration, little more energy has to be spent in order to remove that first electron in the form of first ionization energy. So, this will give some idea about the relative ionization energy of various elements in the periodic table. Let us look into another question, very interesting question, why noble gases have 0 electron affinity. So, this is because all noble gases have completely filled valence shell, that means all the noble gases have S2p6 electronic configuration, and because of this S2p6 configuration all electrons are held firmly and as a result it is very difficult to ionize the electrons to generate cationic species. And since most of the elements have a tendency to attain the next inert gas configuration, because that is relatively more stable and the electrons are much more firmly held by the nucleus, since noble gases do not have any vacant orbital in their valence shell and they have a completed electronic configuration of S2p6, they have no tendency to add another electron. As a result, noble gases have 0 electron affinity. So, let us look into another interesting question. What happens to the size when an atom A is ionized to A plus or A minus and Y? This already we discussed. When we add an electron, a anion is generated, and when we remove an electron, a cation is generated. So, in general, this when you consider the radius A to A plus, it should decrease because the effective nuclear charge increases. Now, remaining electrons are held more firmly by the nucleus. For example, we consider the case of sodium, where sodium atom has 190 picometer as its covalent atomic radius, whereas Na plus has 100 picometer. So, that indicates the decrease in the atomic radius of sodium to become ionic radii of 100 picometer. So, that means going from 3s1 to 2s2 2p6 electronic configuration, there is a huge due to n change, but not in every case. If no change in n, the decrease in the Z effective is always less. So, similarly, let us consider the case of A going to A minus. So, here it is anticipated that ionic radius increases, added new electron without addition of any proton to the nucleus will make the nucleus less effective in holding that extra electron. That means, the decrease in effective nuclear charge is responsible for increase in the ionic radius of any given atom when an electron is added to it. So, let us look into another question. Explain why elemental sulfur forms rings or chains with SS single bonds. We know that sulfur exists as S8 and higher ring form, whereas oxygen exists as a diatomic molecule. So, let us look into the bond enthalpies for the single and double bonds in both the cases. For example, in case of oxygen, it is 142 kilojoules per mole, whereas in case of oxygen double bond, it is 498 kilojoules per mole. And in the same way, we shall look into SS bond enthalpy, that is 263 kilojoules per mole, whereas SS double bond is 431 kilojoules per mole. So, you can see the difference, because OO double bond is more than 3 times as strong as a OO single bond. Oxygen has a tendency to form OO double bond, whereas in case of sulfur, if you just look into this SS single bond enthalpy, it is 263. When it has made SS double bond, the bond enthalpy should have been at least twice the sum of the SS single bond enthalpies. That should have been at least 526, So, instead what we see is 431 kilojoules per mole. So, that means by making a SS double bond, sulfur is not going to gain any extra stability. Instead, by making two single bonds, it can have extra stability. As a result, sulfur exists in the form of S8 ring, whereas oxygen exists in the form of a diatomic molecule. So, let us re-look into some important properties of atoms. In an atom, nucleus is surrounded by electrons in various shells depending on the atomic number. The nuclear charge experienced by the electrons is not uniform and it decreases as electrons are added to the higher shells. So, as a result, the magnitude of the influence of the nucleus on electrons decreases with the increase in the size of the atoms as added electrons are farther from the nucleus. That means, this is due to the shielding or screening of nuclear charge by inner or core electrons. That means, there should be a way to calculate or estimate the effective nuclear charge by each and every electron around the nucleus. That means, we have to have some method of measuring the effective nuclear charge of an atom. For this one, Slater has formulated a new method through some rules to find out the effective nuclear charge. So, let us discuss the Slater's rules and how to determine effective nuclear charge for various atoms or various electrons in their different orbitals in my next lecture. Thank you very much.